কম্পিউটারেও আছি। তো আমার কথা এখন ক্লিয়ারলি শোনা যাচ্ছে, তাই তো?
জি স্যার।
জি স্যার।
Okay, great. So we'll start the class now. Today is our lecture number 3. So I'm going to share my screen now. Do you see my screen now?
Yes, sir.
Okay, good. So today's lecture will be, this is the lecture of the last class. It was lecture 2. Today we are going to talk about lecture 3. Today's lecture is pretty much fundamental, and you need to understand the concepts. You need to understand the concepts. So we will talk about fundamental assumptions of reinforced concrete behavior. We have 5 fundamental assumptions, and if you understand these 5 assumptions, I think we are done for today. Just a second. I think I need to open one more file. I don't find the file, so let's continue with this one. Okay, we have 5 assumptions. I'll spend like 5 to 10 minutes in each of them. So the number 1 assumption is about the equilibrium. So basically, it is about equilibrium. So we assume, I mean, everybody in the world assumes that the internal forces are bending moment, shear force, normal and shear stresses, torsional moments. So these things are created at sections. If you consider a section, I mean, if you cut a reinforced concrete member by taking an imaginary section, you will see the internal forces, bending moment, shear force, and stresses, maybe torsional moments, and so on. So those things are in equilibrium with the external loads. So basically what we assume here is internal forces and external forces make an equilibrium for any part of reinforced concrete structural member. So you are looking at a beam at this moment. So in the top figure, this is the entire beam with some loads. This is a simply supported beam. Of course, it has applied forces and it has reactions. So it has applied forces and it has reactions. And then we cut the beam by this cut surface. এই সারফেসটা দিয়ে আমরা বিমটাকে we cut it into two pieces, and then we are looking at one of the two pieces in the bottom figure. In the bottom figure, we look at one of the two pieces. So this piece has an internal plane. This rectangular cross-sectional surface is an internal plane surface. And internal plane surfaces have stresses. It will have stresses on concrete. It will have stresses, long stresses on steel. So it will have stresses in concrete and stresses in steel. The, the statement of the assumption number one is pretty simple. The statement tells you that we have external forces. I draw them in red color. The reaction is also an external force. So external forces like applied forces and reactions, they all are external forces. And internal forces, here I put them in purple color, internal stresses. We may have compressive stresses like this. We can have also tensile stresses in the steel bars. So the red colored external forces will be in equilibrium with the purple colored internal forces. This is what the assumption one says. It's very simple assumption. It just tells you that external forces are balanced by the internal forces. It is a fact. It doesn't need to be assumed. It happens everywhere. Everywhere in the world, whenever we consider the whole structure or part of the structure, we will have that all the forces are balanced and they are in equilibrium. So this is what we mean by assumption one. This is about equilibrium. We basically mean the internal forces are in equilibrium with the external loads. So this is basically what we mean. The three words. Internal forces are in equilibrium with the external loads. That's all for assumption number one. So the example that you looked at was about a beam. I showed the external forces acting in the beam. The red colored forces are external forces. And I also showed the internal stresses for the beam. They are in equilibrium. If you consider a column, for example, we have cut the column somewhere in the middle, and we are looking at the top part of the column. So here the external force is, this applied force from the top, and we have internal forces since it has been cut. It is cut somewhere. It is cut somewhere here. So say we cut it here into two pieces, and we look at the top part only. So this surface is an internal plane surface. So in this surface, we'll probably have compressive stresses. Of course, there are two materials here. We need to remember always that the reinforced concrete is a composite material. Composite means there are two materials blended here. One material is inserted into another. It is basically concrete, but we have steel bars inserted into concrete. So it's a composite. So composite will behave in different ways than a homogeneous material. Homogeneous material is when there is no inclusion, there is nothing. It has same material everywhere in all three dimensions. It has same density everywhere, same unit weight everywhere, same property everywhere. That sort of material is called a homogeneous material. But here we are not dealing with a homogeneous material. We have a composite. Composite means we have concrete, but at some locations we have steel bars. We have steel bars inside concrete. So composite. So here the stresses will be, some stresses are in concrete. I put them in blue color, and some stresses will be in steel bars. I draw them in purple color. So combined way, all the stresses in concrete and stresses in steel together will be in equilibrium with the external force P. Will be in equilibrium with the external force P. So whatever is the structural member, it could be a column or it could be a beam. If you draw the external forces, all of them, and if you assume the internal stresses correctly, the equilibrium will be there between the external forces and the internal stresses. That's our fundamental assumption number 1. If you understand this one, I will move on to fundamental assumption number 2. Okay, so let us proceed to fundamental assumption number 2. Here. This is about deformation. The first one was about equilibrium. The second one is about deformation. Deformation means, I think we could have written it in a very simple sentence. Let me go back and write it down in a very simple sentence. It means strain in steel bars is equal to strain in surrounding concrete. So basically what we mean that strain in steel equal to strain in concrete. It's a very simple concept, but this concept has the most profound implications in our reinforced concrete behavior and design. We assume, and this is reality. We assume that, but this is reality. We assume that strain in steel bars or strain in steel is equal to strain in surrounding concrete. So let me give you a few illustrations by figures first. Then I'll come back to the statement one more time. So look at this column carefully. So to the leftmost, we have a column that has 4 reinforcing bars inside it. In its interior, there are 4 bars. So the column is acted by a compressive force. So what we expect is due to the application of the compressive force, the column will elastically deform, or basically what we assume, if the length of the column before deformation was L, so let us consider that the length of the column before deformation was L. So after deformation, since it is under compression, it is under compressive force, after deformation, the length of the column will be a little bit smaller. A little bit smaller. Let us consider this smaller length to be L minus delta. Now look at the third figure. Before deformation, the length of the column was L, and after deformation, the length of the column is L minus delta. Delta is its elastic shortening. Elastically, there will be shortening. This sort of shortenings are very small, maybe 1 or 2 millimeters, but it is there. 1, 2, 3 millimeters based on the value of the magnitude of the load, applied load. So what we assume here is the shortening, amount of shortening delta is equal for concrete and steel. So if concrete is shortened by an amount delta, all steel bars also have been shortened by the same amount of delta. So আমি একটু বাংলায় বলি, কংক্রিট এই যে ফোর্সের চাপ খেয়ে কংক্রিট যতটুকু শর্টেন্ড হয়েছে, যতটুকু স্মলার হয়েছে, প্রত্যেকটা স্টিল বার সেই ইকুয়াল অ্যামাউন্ট শর্টেনিং হয়েছে. So the amount of deformation is equal for concrete and steel. Now look at the last figure, the fourth figure. This last figure shows you that concrete has a shortening, but steel bars did not have a shortening. Steel bars have remained longer than concrete. It doesn't happen, so I put a cross here. So basically, the length change is equal for concrete and steel bars. এইরকম ভ্যারিয়েবল লেন্থ চেঞ্জ হবে না. লেন্থ চেঞ্জ স্টিলটাও ছোট হয়ে কংক্রিটের সমান পরিমাণ শর্টেনিং হবে. So this is what we wrote as strain in steel bars equal to strain in surrounding concrete, which means strain মানে amount of length change will be equal for concrete and steel. দুটা equally strained হবে. They will deform together, they will shorten together, and if you apply a tension force, they will elongate together. There will be no difference in their deformation. Their deformation are always equal. So in a few statements, let me tell you now. So fundamental assumption number 2 says the strain in an embedded reinforcing bar, which means bar is inside concrete now, embedded মানে ভেতরে দেওয়া, extension or compression is the same as that of the surrounding concrete, which means strain in the bar, which means basically strain in reinforcing bars is the same as of the surrounding concrete. Basically যেটা আমি লিখেছি, strain in steel bars equal to strain in surrounding concrete. Why does this happen? This happens because there is a perfect bonding exists. Steel bars are bonded heavily. Steel bars are bonded. Steel bars here are bonded heavily with concrete. Steel barke চারপাশ থেকে concrete শক্ত করে আঁকড়ে ধরে রাখে. This is what I express in a layman term in Bangla. Steel bars are bonded heavily by concrete. Concrete holds the steel bars in a very strong bond. So the bond is so strong that between there is a bonding force there is a bonding force. This is basically frictional force exists between concrete and steel at the interface. Interface means, let me draw it for you. Interface means what? তো মোটা করে দিলাম। So there will be bond force. So if there is a tendency of, you know, deformation, this sort of friction between steel and concrete are generated. So that friction stops any sort of relative movement between concrete and steel. So this sort of strong bond stresses, this is basically friction that is created on the outer surface of the cylindrical shape of the steel bars. Steel baরের সারাউন্ডিং cylindrical surface এই ধরনের friction create হয়. That friction stops any sort of relative movement between concrete and steel. So this sort of relative movement in our engineering terminology is called slip. So if there is a slip মানে হচ্ছে if there is a relative movement. For example, in the fourth figure, which has been crossed by me, there was a slip. To properly understand this fourth figure, you should consider something. Hypothetically, তুমি imagine করতে পারো যে here there are 4 steel bars embedded in a foam like material. সোফা সেটের ফোম আছে না, তুমি মনে করো ফোমের এরকম একটা কলাম আছে যার ভেতরে এরকম 4টা স্টিল বার এমবেডমেন্ট করা আছে। Now if you push the foam সোফার ফোমের মতো, if you push the foam downward, what happens? Foam squeezes. Foam squeeze করে নিচে চলে যাবে, কিন্তু স্টিল বার গুলো আগের লেন্থেই থেকে যাবে। So if you squeeze the foam will go down. Foam হয়তো এভাবে চাপ খেয়ে foam shrink করে চলে যাবে, but steel বার গুলো আগের লেন্থেই থেকে যাবে। So this means the foam had a slip, slip with the concrete. ফোমটা যখন shrink করতেছে, সে নিশ্চয়ই স্টিল বারের গায়ে ফ্রিকশন করে করেই ফোমটা স্কুইজ করেছে। So what we are assuming for concrete is concrete does not squeeze in respect to steel bars. Concrete steel বারের রেসপেক্টে কোনো ধরনের স্কুইজ করে না। concrete এবং steel equally deform করে. So there is no relative movement between steel and concrete. So that relative movement in our term, we call it slip, SLIP, slip. So there is no slip between steel and concrete. So as one deforms, একটা যদি deform করে, so must the other. If concrete deforms, steel also deforms. If steel deforms, concrete also deforms. They cannot deform separately. They deform together. They elongate together. They contract together. So extension or compression, elongation or contraction happens together. There is no relative movement between steel and concrete. So this is maintained by this high degree of mechanical interlocking, because you know the bar surfaces are ribbed burst surfaces are deformed. We call them deformed bursts. So their deformed bursts are interlocked with the aggregates of concrete, and they don't let any relative movement in addition to the natural adhesion between cement and steel. So this is very close to the correct situation. So for a column, we assume it this way, that the fourth thing doesn't happen. The fourth thing doesn't happen. The third thing happens. Concrete and steel has equal shortening or equal elongation. If you consider a beam under bending moment, this is what we assume to take place in a beam. When you take a cross section, consider that this is the cross left part of a beam, which is created by taking a section somewhere here. So this plane surface is an internal plane, and there is a bending moment. Maybe there is a shear force and axial force. We are not considering them at this moment. We are considering only the bending moment. By the way, are you listening?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Yes, sir.
Very good. We have 53 students at this moment, or 54 students. I have two devices, so Masjidul Arash just joined. Why?
স্যার আমি আগেও জয়েন করছিলাম স্যার, নেট প্রবলেম ছিল, আবারও ঢুকছি।
নেট প্রবলেম তো থাকে না বাংলাদেশে এখন।
স্যার আমি বাইরে তো স্যার, এই জন্য স্যার, সরি স্যার।
বাইরে মানে কোথায় তুমি?
স্যার হাটে আসছি স্যার, সরি।
তোমাকে আমি রিমুভ করে দিচ্ছি। গরুর হাটে থেকে তুমি কেন ক্লাসে জয়েন করেছো?
সরি স্যার।
এটা কি ফান করা না?
না স্যার, সরি।
আর কেউ আছো নাকি তুমি গরুর হাটে? এখনো থাকলেও বলবে না। Acha, let's go back. So this is probably a left portion of the beam that is acted by a bending moment. So what a bending moment does to the beam? What it does, here, due to the application of this bending moment, this vertical surface, this cross-sectional surface, which is vertical now, will undergo a rotation. Vertical surface ta rotate kore erokom hoye jabe. So at the end of application of the bending moment, we will find that the surface, that the internal surface that was vertical before now has become an inclined surface. যে সারফেসটা আগে ভার্টিক্যাল ছিল before the bending moment was applied, it will become an inclined surface like that. So if the surface is inclined, and if you compare it with the previous one, if you superimpose, let us put it on the surface here. So if you, this was the previous condition, the yellow one. So the vertical surface was the situation before bending moment was applied, and after the bending moment is applied, the vertical surface has been rotated and gone to this inclined surface. So if the surface is rotated, you should understand that the top portion, I mean from this 0 point upward, this whole portion, this top portion of the beam is acted by compressive strains, and the bottom portion is acted by tensile strains. Who is this? Hmm? ASS, who was this? Asir. Asir Hamim Mustafa.
Yes, sir.
তুমি কি একটু আগে কথা বলতে চাচ্ছিলা?
No, sir.
Okay, let's come back. So the top portion is compressed inward and the bottom portion is elongated outward. So let us concentrate ourselves with the bottom portion only. So concrete to the bottom portion is elongated. Maybe the most extreme portion of the bottom of the concrete is elongated maximum, and the elongation, the amount of elongation reduces as you go up, and elongation is 0 at the neutral axis. But there is an elongation at the location of the steel bars. So steel bar গুলো যেখানে আছে সেখানেও concrete elongated হবে due to the application of bending moment. So if concrete is elongated at this portion, you should look at my mouse pointer. You should look at my mouse pointer. So a concrete যেখানে steel bar গুলো located, সেই লোকেশনেও concrete elongated হবে. So concrete যদি elongated হয়, সাথে সাথে steel bar গুলো elongated হবে. This is what is assumed in assumption number 2. ওই যে বলেছিলাম strain in steel is equal to strain in surrounding concrete. There will be no slip. So here, when concrete is being elongated to the tension zone due to bending moment, steel bars also elongate. And the thing that is shown in the final figure, fourth figure, does not happen. This figure shows that in the tension zone, concrete has been elongated, but steel bars are maintaining the same length in when it was moment was not applied. So it does not happen, it is cross. Steel bars cannot maintain the same length. It must elongate along with concrete as concrete is elongated and contracted due to the application of bending moment. Do you understand this? So let me go back to the statement of the assumption number 2. In a very short term, it means strain in steel bars equal to strain in surrounding concrete. And in detail, it means there is a perfect bond exists between concrete and steel at the interface. Interface means outer cylindrical surface of the steel bars, so that no slip occurs between the two materials. As one deforms, so must the other. So this happens due to the mechanical interlocking. So in an illustration, we applied an external force to the concrete column, and concrete column undergoes a length change. If the length previously was L, now the length is L minus delta. So concrete has been shortened by an amount delta, and so must the steel bars. Steel bars গুলো same amount of delta shortening এর মধ্যে দিয়ে যাবে. Steel bars also will undergo the same amount of shortening. And the fourth thing doesn't happen. Concrete খুব বেশি shortened হয়ে যাবে, steel bar shortened হবে না বা কম পরিমাণ হবে, unequal shortening হবে. It doesn't happen. Shortening, the deformation will be equal between concrete and steel. This happens for compression. This also happens for tension when concrete is acted by bending moment. So bending moment এর কারণে যদি যখন একটা vertical surface vertical cross-sectional surface undergoes a rotation like this, so some portions of the concrete is compressed due to the compression, and some portions of the concrete is elongated due to tension. We are focusing on the tension zone only. In the tension zone, concrete is elongated, so it must take the steel bursts with it. Steel bursts will also elongate by the same amount of elongation. So this fourth figure doesn't happen. Fourth figure shows that concrete has elongated, but steel bursts are maintaining the same length. It doesn't happen. The amount of elongation in concrete and in the steel bursts in the same location will remain the same. That is what we mean that strain in steel bursts equal to the strain of its surrounding concrete. So that's our assumption number 2. You try to understand it. Now we'll move on to assumption number 3. Assumption number 3 is something that we already have gone through. Assumption number 3 টা আমরা already pass করে গেছি, but mention করি নাই. So let me tell you briefly, এটা খুব সময় লাগবে না. It means cross sections that were plain prior to loading will remain plain when the member is under load. So this is what we already have gone through. Simple. So this vertical surface, the cross section, this cross section was a plane surface. It is a parallelogram, or parallelogram draw করলেও 3 dimension. Basically it's a rectangle. It's a rectangle. It's a rectangle. Let us put some names. মনে করো this is rectangle ABCD. So we are focusing on the cross-sectional surface ABCD at this moment. So after deformation, the surface ABCD, maybe ABCD goes to a new location, the whole thing compresses, but it remains a plane surface. It remains a rectangle. The surface doesn't change. Their surface remains plane also mean that there is no undulation. Undulation means there is no undulation means which means no warping. No warping. মানে সারফেসটা এবড়ো খেবড়ো হয়ে যাবে না. Surface will remain plane surface. So there is no undulation, no warping. সারফেসটা উইল কোনো অ্যাপারচার হবে না, এটাকে আমরা কংক্রিটের ভাষায় বলি অ্যাপারচার, এবড়ো থেবড়ো হবে না আর কি। Surface will remain plain surface. So it happens to column, it also happens to beam. Oh, column, even if you apply a bending moment, in the last figure we applied only a concentrated force. If you apply a bending moment, the surface ABCD undergoes a rotation. So ABCD,
স্যার
yeah,
স্যার আমরা কি এখানে বেসিক্যালি মানে এই জিনিসটা অ্যাভয়েড করছি যে যখন ডিফরমেশনটা হবে তখন আমাদের উইডথটা যে বাড়বে ওটা আর বাড়বে না আর কি স্যার, রাইট? মানে উই আর অ্যাজিউমিং ইট, রাইট?
yeah, we are assuming that Poisson's ratio actually
Yes, sir.
is
Yes.
negative here. There will be
Okay.
no elongation to the lateral direction. Yeah.
রাইট, থ্যাংক ইউ।
So when bending moment takes place, maybe the surface ABCD rotates and go to a new orientation like A prime, B prime, C prime, D prime. But again, this surface, the inclined surface, is also plane surface. The inclined surface is also plane surface. Again, there will be no undulations, no warping, no aperture. Although this is not absolutely correct. There are some sort of warpings and some apertures are there, but we ignore them when we design them. When we design reinforced concrete structures, when the surface, the rectangle ABCD undergoes a rotation and goes to a new orientation, A prime, B prime, C prime, D prime. And you understand, as I told before, that আমি একটু ফোনটা ধরে আছি, হ্যাঁ। Okay, I joined one more time. Do you hear me? শোনা যাচ্ছে?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So let us continue where we left out, left off. Screen share করা যাচ্ছে. So আমি যেটা বলছিলাম যে this assumption is not 100% correct. So accurate measurement যদি করা যায়, if you measure accurately, have shown that when a reinforced concrete member is loaded close to failure, this assumption is not absolutely accurate. However, the deviations are usually minor, and the results of theory based on these assumptions check well with extensive test information. I want to emphasize on this particular term, test. We need to understand that concrete more or less does not follow any mathematical formula. Most of the time, concrete does not follow any mathematical formula. So to understand concrete behavior properly, I mean to understand its real behavior, we need to go to the laboratory and do some tests. So we have found that during very close to failure, this assumption is not 100% correct, but the deviations are minor. And the results are, they check well with the extensive test results. So what we are assuming here, that all the cross sections, for example, for the column, we have a rectangular cross section ABCD. So it is compressed, but ABCD remains ABCD. There is no undulation, no warping, no aperture. It remains absolutely plain. Similarly, when a column or beam undergoes a rotation due to bending moment, now ABCD, the surface, cross-sectional surface, has undergone a rotation and went to a new orientation, A prime, B prime, C prime, D prime, but still the surface A prime, B prime, D prime, C prime remains a rectangle. Still remains a rectangle, although inclined rectangle, but it's a rectangle. And it is plain. There is no warping, no aperture, no undulation. It is absolutely plain. So this is our assumption number 3. Now assumption number 4. This is pretty simple, although I wrote a lot of information here, but the assumption is pretty simple here. As you understand from the beam behavior, let me go back and show the beam behavior here. So when a beam is acted by a bending moment, the cross section undergoes a rotation. Bending moment মানে এটা beam hook, column hook, the cross section will rotate. The cross section will undergo a rotation. So when it rotates, you understand that some part of the beam are being pushed inward. I showed a force here. Some part of the beam is pushed inward. So when someone pushes a material inward, we call it a compression. So some portions of the beam is under compression, and some other portions of the beam are being pushed outward. So there is a force. There are two forces. One is compression, one is tension. They are parallel. They act toward opposite directions. They create a couple, and couple moment is equal to the applied bending moment mx. That is one side of the discussion. Here we are concentrating again on the tension zone. We need to understand that I told you in the classroom that concrete is very strong in compression. So in the compression zone, whatever is the force, the concrete can take a very large value of force. Concrete is strong in compression. It doesn't break down. It doesn't collapse. It doesn't fail. It doesn't crush easily under compression. But when you apply a tension force to concrete, you need to understand that concrete is weak in tension. So when you apply a tension force, concrete cannot take that much tension. So what happens? Concrete fails under a very small amount of tension force. So when it fails, what happens? When under a very small amount of tension force concrete fails, we see this sort of cracks. এই যে crack দেখা যাচ্ছে না? Crack, 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 all crack. So these cracks are so many that they're like numerous cracks. So concrete to the tension side is always cracked. Is always cracked. Usually these cracks are very small in size. We call them micro cracks or hairline cracks. Hair mane chul. Hairline cracks. Chuler line moto chikon cracks. But these cracks are everywhere. All the concrete structures that you use, your concrete buildings, your concrete bridges, flyovers, expressway, elevated expressway, whatever, all the concrete structures are cracked. So cracks are everywhere. Concrete is designed to crack. We expect cracks in concrete. If concrete is not cracked, it is not a good design. So we will assume that concrete to the tension side is always cracked. So here we wrote that the tensile strength of concrete is only a small fraction of the compressive strength. So concrete in that part, mane tension part of a member which is in tension is usually cracked. Basically, tension zone is cracked. Concrete tension zone is cracked. So in well-designed members, they are generally so narrow to be hardly visible, so we don't see them because of painting and everything. We don't see them. So they are hairline cracks. They're very narrow in dimensions. So if there are cracks, we need to understand that concrete is not, etar dike tako, if concrete is cracked everywhere, concrete basically is not carrying any tension force. All the tension force are being carried by steel bar. So concrete does not carry any tension force when it is cracked. All the tension forces are carried by steel bars. So when we design a reinforced concrete member, we need to understand that we design the tension zone to be resisted by steel bars only. We design the tension zone so that the tension force is resisted by steel only. Concrete does not resist any tension force. This is our assumption number 4. Now the final assumption. Final assumption is simple. The theory is based on the actual stress-strain relationships and strength properties of the two constituent materials. So when we shall design, we shall start design from the next class. By the way, do we have a class on Wednesday?
Yes, sir.
Yes, sir.
Yes, sir.
Wednesday class is very important. I will explain all the fundamental things. So কেউ যদি গরু বাজারে যাও Wednesday you will lose it. Don't do that. ঈদের আরো 4-5 দিন বাকি আছে, আজকে গরু বাজারে গেছে কেন? So fundamental assumption number 5 means there are two materials here. One is concrete, one is steel. So we know that the stress strain diagram of steel is like this. It starts at some point, up to some point, steel is following Hooke's law, stress and strain are proportional. Steel is also elastic. Then it yields, this yield plateau is quite long. Then it goes to strain hardening. So basically, this is the stress strain relation for concrete. By the way, strain hardening portion is curved, not a straight line like me, like the thing that I draw. This portion is curved. So although it's a composite, we will still consider this traditional stress strain diagram for steel, and we will also consider the traditional stress strain diagram for concrete. So before you come to the next class, I want you to learn the stress strain behavior of steel and concrete properly. Concrete behave this way, steel behave that way. We shall follow this stress strain diagram for steel and this stress strain diagram for concrete. We are not going to develop some new diagrams. And the definition of stresses will remain the same. For example, in your solid mechanics class, you learned axial stress, you learned bending stress, and you learned shear stress. We will be using this formula again. We are not going to develop some new formulas. So that's the basic concepts of today's class. If you have any question, I will answer that. But you start thinking what could be your question. In the meantime, I will take the attendance.
স্যার স্যার অনেক জায়গায় তো স্যার ক্র্যাক স্যার দেখা যায় না, তাইলে কি স্যার সেগুলো কি স্যার খারাপ? মানে
কি দেখা যায় না?
মানে ক্র্যাক তো স্যার মানে সব জায়গায় দেখা যায় না, মানে যেগুলো স্যার দেখা যায় না তাহলে কি স্যার সেগুলো খারাপ?
গ্রাফ দেখা যায় না?
ক্র্যাক ক্র্যাক
স্যার ক্র্যাকস এর কথা বলতেছে।
স্যার ক্র্যাক স্যার
Cracks.
Crack দেখা যায় না? No, it's okay. Cracks, these are micro cracks, these are hairline cracks. You are not supposed to see them. যদি কোনো crack দেখা যায়, this will be discussed in future classes. If you really see some cracks, the structure is not usable. You should evacuate the structure. Crack দেখা যায় না সেটা ভালো কথা. Crack দেখা গেলে বিপদ.
ওকে স্যার।
Okay, attendance দাও. খালেদুজ্জামান,
yes sir
তাসলিম, রুবায়াত,
প্রেজেন্ট স্যার।
কাজী ওবায়দুল্লাহ
Present,
আল
sir.
আবিদ, আব্দুল্লাহ আল মামুন। এই ওবায়দুল্লাহ, কাজী ওবায়দুল্লাহ,
ইয়েস স্যার।
তুমি তো মনে হয় রাস্তায় বাইরে গরু বাজারে কোথাও।
জি না স্যার, আমি আর কি হচ্ছে বাসে যাচ্ছিলাম, ট্রাভেল করতেছি স্যার।
ট্রাভেল করতেছো বাসে?
জি স্যার।
আচ্ছা, Abdullah Al Mamun, absent. Abir Hussein Liloy,
প্রেজেন্ট স্যার।
তুমি কোথায়?
স্যার বাসায় স্যার।
SM Sajjadul Maula,
Present, sir.
MD Abu Zor Musaddiq,
ইয়েস স্যার।
Rakib Hussein,
প্রেজেন্ট স্যার।
Arafat Shahwar,
প্রেজেন্ট।
Dipranita Josephine,
Present, sir.
Shahriar Siddiqui,
Present, sir.
Mahadi Alam Rafi,
Present, sir.
Nuzhat Tabassum Jannat,
Sir.
Shafkat Junaid,
Present, sir.
Tanjina Islam Afrin,
Present, sir.
Zahid Hassan Munna, Zahid Hassan Munna is absent. Nazifa Tasnim,
Present, sir.
Ryan Murshid Bhuiya,
Yes, sir.
MD Shihab Shahriar,
Present, sir.
Irani Tasnuva,
Present, sir.
Saida Jannatul Bushra,
Present, sir.
Asir Hamim,
Present, sir.
Amit Kumar Das,
প্রেজেন্ট স্যার।
MD Imtiaz Alam Lamim,
প্রেজেন্ট স্যার।
Abir Rahman Nibir,
Present, sir.
MD Masudur Rahman, absent. Shakil Ahmed,
প্রেজেন্ট স্যার।
MD Aryan Shikdar Ramim, absent. Ahmed Shibli Zim,
Present, sir.
Marjia Haq Hea,
Present, sir.
MD Fardin Bhuiya,
প্রেজেন্ট স্যার।
Munabi Binte Maqsood,
Present, sir.
Nasikh Alvi,
প্রেজেন্ট স্যার।
MD Ikramul Haq, absent. Fahim Ahmed,
প্রেজেন্ট স্যার।
Firdaus Mahmud, মুনাবি বিনতে মাকসুদ তোমাকে প্রেজেন্ট দিয়েছি, হ্যান্ড রেজ করার দরকার নেই আর। ফিরদৌস মাহমুদ, অ্যাবসেন্ট। শাহিদ মুর্শিদুল হক,
Present, sir.
সামিহা বিনতে বাশার,
Present, sir.
জাসিন আহমেদ, মাইক নাই, ঠিক আছে। MD আহনাফ হাসান, প্রেজেন্ট, বুঝলাম। খন্দকার সাদমান সাকিব মাহি, সাদমান সাকিব মাহি is absent. MD মাহমুদুল হাসান শাওন,
Present, sir.
MD তানজিল আক্তার,
Present, sir.
শরীফ MD আলী রাকিব,
প্রেজেন্ট স্যার।
MD মেহেদি হাসান কনক, মেহেদি হাসান কনক তো প্রেজেন্ট মনে হচ্ছে।
প্রেজেন্ট স্যার।
SM শাহরিয়ার ফয়সাল শিশির,
Present, sir.
ইমামিম মুবিন,
ইয়েস স্যার।
নিলয় দাস চমক,
প্রেজেন্ট স্যার।
SM মাশরাফি, Mashrafi absent. MD Shamim.
Present, sir.
MD Masjidul Arash. Masjidul Arash absent. Arman Hussain.
প্রেজেন্ট স্যার
MD Mustaqin Hussain Mugdho.
Present, sir.
Sadman Saqib. Sadman Saqib absent. Fahad Islam. Fahad Islam absent.
Sir,
Mashir
present,
Rahman.
sir. Fahad Islam present.
Dilam. Mashir Rahman Chaudhary.
Present, sir.
Mahia Ahmed.
Yes, sir.
Shahriar Parvez Deep.
Present, sir.
MD Moshir Rahman PL. SF Mashrafi, তুমি কি এইমাত্র জয়েন করেছো?
না স্যার, আমি ছিলাম, এখন আস্তে আস্তে হঠাৎ আমার বের হয়ে গেছিল, আবার তাই করলাম।
মশিউর রহমান পিয়াল। আয়ান জামান।
Present, sir.
মাহিন মুন কাতিন সিজার।
Yes, sir.
রুফায়দা হোসেন চৌধুরী।
Present, sir.
তানভীর রহমান সামি।
Present, sir.
আব্দুল্লাহ আল জাবিদ।
Present, sir.
আল শাহরিয়া ইসলাম সিয়াম।
Present, sir.
ওকে, কারো কোনো কোশ্চেন আছে? We have assumption 1, which is equilibrium. External and internal forces are balanced and in equilibrium. Assumption 2 is strain in steel equal to strain in concrete. So there is no slip. Deformation in concrete is equal to deformation in steel. Assumption 3 is cross sections remain plane. ABCD remains ABCD. There is no warping, no aperture. Cross section does not change. Maybe cross section is inclined due to moment, but it remains a plane. Plane surface remains a plane surface. Assumption 4 হচ্ছে concrete is cracked in the tension zone. Assumption 5 হচ্ছে we will use the stress-strain relationship of the constituent materials, steel and concrete. Then when we go to our design problems in the next class, we shall calculate stresses based on these formula. Okay, so this was our lecture 3, but we left something in our lecture 2. I couldn't finish it in time. Lecture 2 একটু part বাকি রয়ে গেছে. If you remember lecture 2, we talked about loads, dead load, live load, environmental load, wind, earthquake. I think here I didn't discuss this thing. We use some sort of safety provision. CEE safety provision is here. Design strength should be equal to nominal strength multiplied with strength reduction factor. So this is what we discussed in our last class. At one calculation, at one set of calculation, we draw the structure's geometry. Basically, we model it in software. Then we apply loads in their load combinations. There are 8 combinations. So we combine the loads in various ways: dead load, live load, dead load, live load, roof live load, snow load or rainwater load, dead load, roof live load. LR মানে roof live load, S for snow বাংলাদেশে নাই, R for rainwater বাংলাদেশে আছে, then live load or wind load, wind W for wind, and this S for seismic. No, this is for snow load. Seismic is E for earthquake. So we apply loads in all their 8 combinations. So every time you draw the bending moment diagram for a certain member, you need to draw 8 bending moment diagrams for different 8 loads. Every load is combination of dead, live, wind, earthquake, snow, rain, and so on. So you analyze your structure 8 times every time you need to design it. So after analysis kore, you analyze the structure for all load combinations, and then you determine the axial force, shear force. Basically, when you determine, you basically draw the diagrams. SFD, BMD, draw kolla. Then from the diagrams, you take the maximum. So you have 8 sets of diagrams, and you consider the maximum from all 8 sets combined. Then you determine, this is called required strength, PUVU, means required bending moment, required shear force, required axial force. Okay, this is what we shall not do in our course. এই কাজগুলো আমরা এখানে করব না, এই কাজগুলো আমরা হয়তো C330L বা 335L ওগুলোতে করব। আমরা যেটা করব সেটা এই জায়গায়। So in this course, we will determine or select a cross-sectional size and reinforcements. আমরা একটা cross-sectional size determine করব, calculation করব, অনেক calculation করে we will determine the size or we select a size. Then we will determine the capacity of the cross-section in terms of axial force, shear force, and bending moment. When we say capacity, we mean the value of the load that will cause it to fail. So whenever you are applying moment to your member, the member fails when the moment is Mn. Or when you apply shear force to a member, the member fails when the shear force value is Vn, and so for axial force. So Pn, Vn, Mn reach korle মেম্বারটা ফেল করে। তো নিশ্চয়ই আমরা পিএন, ভিএন, এমএন ওই পর্যন্ত অ্যাপ্লাই করব না, আমরা তার চেয়ে একটু স্মলার ভ্যালু অ্যাপ্লাই করব। সেই স্মলার ভ্যালুটা আমরা ফাই দিয়ে ডিটারমিন করি, ফাই দিয়ে মাল্টিপ্লাই করলে যে ভ্যালু পাওয়া যায়, দ্যাট উইল বি আওয়ার ডিজাইন স্ট্রেংথ। সো আমরা ফাই এর ভ্যালুগুলো এসিআই থেকে নিয়ে নিব। মোমেন্টের জন্য 0.9, শিয়ারের জন্য 0.75, axial force এর জন্য 0.65, আর বাকিগুলো আছে পরে আমরা দেখব। So this is what we shall do in our class. আমরা একটা একটা করে এই কাজগুলো করব। যেমন আমরা নেক্সট ক্লাস থেকে we will start calculation of moment, Mn. আমরা মোমেন্ট দিয়ে শুরু করব নেক্সট ক্লাসে। Okay, but if you maintain these criteria, এই ক্রাইটেরিয়া গুলো মেনটেন করতে পারলে your member is structurally safe. বাট সেফটি ছাড়াও আরেকটা ইস্যু আছে, সেই ইস্যুটা হচ্ছে সার্ভিসিএবিলিটি। সার্ভিসিএবিলিটি আমরা এখনো 100% ফলো করি না, বিকজ এসিআই কোড এখনো, ইভেন আওয়ার বুক দ্য 16th এডিশন, সেখানেও সার্ভিসিএবিলিটি রিকোয়ারমেন্ট গুলো ডিজাইনের মধ্যে নিয়ে আসে না। বাট স্লোলি দে উইল বি হিয়ার ইন দ্য কোড। এখনো পুরোপুরি আসে নাই, এখন এসছে যেটা ছিল ডিফ্লেকশন। সো in addition to axial force, shear force, and bending moment, we need to consider deflections. Deflections should be small. You think about a building, যে একটা বিল্ডিং তুমি থাকো, you stay in a building, but when you enter into the room, that room undergoes a deflection. তুমি একটা ব্রিজের কথা চিন্তা করো, when you pass over the bridge by a vehicle, the bridge either deflects or vibrates. It does not give you a good feeling. যেটা স্টিল ব্রিজে সবসময় হয়, তুমি যখন একটা স্টিল ব্রিজের উপর দিয়ে ট্রেনে করে যাও, ইউ মাস্ট ফিল যে ব্রিজটা ভাইব্রেট করছে। বাট কংক্রিটে এই ধরনের ভাইব্রেশন আমরা অ্যালাউ করি না। এই ধরনের ভাইব্রেশন অ্যালাউ করলে আমরা বলি যে দিস স্ট্রাকচার ইজ নট সার্ভিসিয়েবল। সো কংক্রিট স্ট্রাকচারের কন্ডিশন হচ্ছে deflection should be very small so that it does not give you a feeling that when your structure is deflecting a lot, you will feel unsafe. তুমি একটা মসজিদে গেলা শুক্রবারে, প্রচুর মানুষ বসে আছে, দেখলা যে মসজিদের ফ্লোরটা একটু কার্ভড হয়ে গেছে, নিচের দিকে কার্ভড হয়ে গেছে। মেবি মানুষ উঠে চলে গেলে ফ্লোরটা আবার স্ট্রেট হয়ে যাবে, ইলাস্টিক ডিফরমেশন তখন চলে যাবে। But even if it comes back to its previous flat position, it doesn't mean that it doesn't give you comfort. People will feel discomfort and people will be scared basically. মানুষ ভয় পাবে যে এটা বুঝি ভেঙে পড়ছে। সো এই জন্য কংক্রিট স্ট্রাকচারের নিয়ম হচ্ছে ডিফ্লেকশন শুড বি ভেরি স্মল, ভাইব্রেশনস শুড বি মিনিমাইজড। ভাইব্রেশন যেন না করে, ব্রিজগুলো এলিভেটেড এক্সপ্রেসওয়ে দিয়ে যাওয়ার সময় যদি এটা সারাক্ষণ ভাইব্রেট করে, it does not give you a very good feeling. So vibration should also be minimized. And as I mentioned today, একটু আগে যখন মেনশন করলাম, একজন একটা কোয়েশ্চেনও করেছিল যে আমি বলেছি যে কংক্রিট ইন দ্য টেনশন সাইড ইজ অলওয়েজ ক্র্যাকড, বাট মনে রাখতে হবে these cracks should be very very small hairline cracks বা micro cracks. They should not be visible. If you see visible cracks in your structure, maybe the structure is still safe, but it gives you some anxiety. Crack যদি বড় বড় দেখো, যারা স্ট্রাকচারটা ইউজ করে তারা একটু ভয় পাবে। সেজন্য if there are cracks, they should be within some tolerable limits so that people do not get scared. So these three requirements are called the requirements of serviceability. That deflection, crack এবং vibration, এই তিনটা জিনিস মিনিমাইজ থাকতে হবে। সো আমরা যেটা করি, ওই যে বললাম একটু আগে, টু ক্যালকুলেট দ্য রিকোয়ার্ড স্ট্রেংথ, উই মডেল দ্য স্ট্রাকচার ইন এ সফটওয়্যার, এটা স্ট্যান্ডার্ড সফটওয়্যার থেকে নেওয়া। উই মডেল দ্য হোল থিং instead, then we analyze it, we apply loads in their all combinations, সবগুলো কম্বিনেশনে আমরা লোড অ্যাপ্লাই করে দিই। And when you analyze it, it analyzes the structure for all loads. Load combination 1, load combination 2, load combination 3. এই সবগুলো কম্বিনেশনের অ্যানালাইসিসটাই করা হয়, করে ম্যাক্সিমামটা নোট ডাউন করা হয়। So this is an axial force diagram of columns. So we took the maximum value. That is called the required strength. Then in another set of calculations, which is usually hand calculation. So এই ক্লাসে আমরা যেগুলো করব সেগুলো সবই হ্যান্ড ক্যালকুলেশন। We shall not do any computer analysis here, but hand calculation করার জন্য usually we use some sort of codes. তুমি যে কোড পছন্দ করো, you can use MATLAB, you can use Mathematica, you can use C+, you can use even Microsoft Excel, but you can use any code for your own hand calculations. আমরা সফটওয়্যার দিয়ে অ্যানালাইসিসটাই করি, আর হ্যান্ড ক্যালকুলেশন বা কোড ইউজ করে আমরা ডিজাইনটা করি। In our next class, we shall start our design. I think that's it for today. So I'll see you in next class. কারো কোনো কথা থাকলে বলতে পারো।
স্যার আমার একটা কোশ্চেন আছে।
হুম,
স্যার হেয়ারলাইন ক্র্যাকস আর হোয়াইট ক্র্যাকস এর ভিতরে কোনটা অ্যাকসেপ্ট করতে পারি আর কোনটার জন্য আমরা ইমিডিয়েট অ্যাকশন নিতে পারি?
হেয়ারলাইন ক্র্যাকস এর জন্য কোনো অ্যাকশন নেওয়ার দরকার নেই। হেয়ারলাইন ক্র্যাকস আর অ্যাকসেপ্টেবল।
আর হোয়াইট ক্র্যাকস এর জন্য আমাদের তখন ইমিডিয়েটলি একটা অ্যাকশন নেওয়া লাগবে।
অ্যাকশনের কিছু নাই, only the action is you have to evacuate the structure. If you see structural cracks wide enough, you should evacuate the structure. Structureটা ইউজ করা যাবে না।
স্যার আমরা যে বিমের মোমেন্টের একটা ডায়াগ্রাম দেখলাম, ওখানে যে আমাদের টেনশন পার্টটা স্যার, ওইটা কি সবসময় যেখানে আমার স্টিল বার আছে ওইখানেই হবে?
ইয়েস এক্স্যাক্টলি, কারণ আমরা প্রথমে ক্যালকুলেশন করে বের করব কোন লোকেশনে টেনশন আসছে, সেটা জেনে ওই লোকেশনে আমরা স্টিল বার গুলো বসিয়ে দিব।
ওকে স্যার।
আমরা তো আগে জানবো তো কোন লোকেশনে টেনশন আসবে, সেই লোকেশনে আমরা রড দিয়ে দিব। দেন
থ্যাংক ইউ।
ওকে, আইল সি ইউ অন ওয়েডনেসডে। অলরেডি অনেকেই চলে গেছে, এখন অল্প, আমার মনে হয় 10 জনের মতো অলরেডি লিভ করেছে, অ্যাটেন্ডেন্সটা নেওয়ার পর পরই চলে গেছে আর কি। ঠিক আছে, বাই।
আসসালামু আলাইকুম স্যার।
ওকে স্যার।
আসসালামু আলাইকুম।